Today's lesson is how to write a number as a product of prime factors. Now that title can be a little bit intimidating because it's pretty long, but basically what we're doing here is a term that's called prime factorization. Make sure you've got that written down right underneath your title in your notes. All right, let's get some vocabulary down here. As we have learned in class, a prime number is a number whose only factors are 1 and itself. An example of that would be 7. The only way to build 7 with factors, meaning numbers that you can multiply together to get a number, is 1 times 7 or 7 times 1. We would also say that 7 only has one rectangular array. 1 times 7 would look like this. 7 times 1 would look like this. But we can see that it really is the same array there, just turned a different direction. Whereas a composite number is a whole number greater than 1 that has more than 2 factors. In other words, it can be built with factors in a different way besides itself times 1 or 1 times itself. If 6, as an example, were prime, then its only ways of building it with factors would be 6 times 1 or 1 times 6. But we know that we can build 6 another way using the factors 2 and 3. Therefore, all the factors of 6 would be 1, 2, 3, and 6. And that means there are more than 2 factors. 6 has 1, 2, 3, 4 factors. So it is considered composite. That also means that it could be drawn with more than one type of rectangular array. Depending on if you drew it horizontally or vertically, showing the factors 1 and 6 would look something like this. Whereas you can build a completely different shape of rectangle using the factors 2 and 3. So that's the difference between prime and composite numbers. Let's talk more about composite numbers now. All right, take a look at these different types of trees. Trees can be classified or grouped according to their shape. And we can see lots of different types of shapes of trees. Now, these are not the species of trees like pine or oak, but these are the different types of shapes that trees make. What we're going to be talking about today in math are factor trees. And we're going to be looking at this shape right here. So you can see that the root word of this would be pyramid, because this tree makes a shape that is kind of like a pyramid. And then AL at the end means relating to. So relating to a pyramid. So this would be pronounced pyramidal. Pyramidal. We're going to be taking a look at some shapes that are also pyramidal as we build our own factor trees. All right, so to start with, draw yourself a pyramidal tree. And now we're going to show how we can make a factor tree look like a Christmas tree. All right, if we had the number 18, which is composite because it has more factor building blocks than just itself and 1, we could make it into a tree. Check it out. What if we decided to break 18 into the factors 2 times 9? That's one way that we could decompose 18. 2 times 9. Now, here's what we need to do. So what we need to do now is we need to figure out if every branch of our factor tree needs to end with a prime factor, we need to figure out, have we reached the end of the branch yet? Well, let's take a look at what we've got. We have a 2 and we have a 9. Are either of these prime? Yeah, 2 is prime. You can't break down 2 into any other factors besides itself and 1, so it's prime. So let's circle it. Now what about 9? Are we at the end of the branch yet? Or can we break it down into other factors? Well, we can break it down into other factors. In fact, we can do 3 times 3. All right, now we have to decide, are we at the end of the branch yet? Can we break down 3 into any other factors besides itself and 1? In other words, is it prime? It is prime. So always ask yourself, if it's composite, we're not at the end of the branch. But if it's prime, we are. And so we can see that we've kind of made this pyramid shape with our factor tree. All right. So how can a factor tree be helpful in writing out the prime factorization? What we'll do is we'll look at where each branch of our tree stopped. It stopped here at 2, it stopped here at 3, and it stopped here at 3. So our prime factorization is going to look like this. 2 times 3 times 3. This is how you can write a number like 18 as a product of prime factors. Product means the answer to prime factors. And if you think about it, you can always check your work by actually solving this problem. 2 times 3 is 6, times 3 is 18, right where we started. Now, I've run out of room, but you just continue your notes right below this prime factorization of 18 as 2 times 3 times 3. Okay, a math pro would take a look at this and say, hey, I can write this in a different way. I can use exponents, those little floating numbers. I have 3 times 3. That's the same as 3 to the second power, or 3 squared. And then I can't forget about this 2. So this could be 2 times 3 squared. Or because of the commutative property, my goodness, 3 squared times 2 would get us the same answer. So a math pro would use exponents whenever possible. So be looking for opportunities for that. Remember, that little floating exponent basically means, how many times do you see it? 1, 2 times. Now, just like there are lots of different types of pyramidal trees out there in our environment, there are lots of different types of factor trees as well. Some of you might have been thinking to yourself, hey, I would have actually broken up 18 in a different way. Maybe you were thinking that you could decompose 18 into 3 times 6. Hey, we should be able to get the same end results by doing this different ways. Let's see if it'll actually work. Okay, so we need to ask ourselves every step of the way, am I at the end of a branch yet? In other words, do I have a composite number where I need to keep going, or do I have a prime number and I can stop? What about 3 and 6? Are either of those prime and we can stop, or are they both composite and we need to keep branching down? 3 is prime. We cannot decompose this into any other factors besides 3 and 1. So we're done with that branch. All right, what about 6? 6 is composite, which means we need to keep branching. All right, so you could write the factors of 6 as 2 times 3, or you could write it as 3 times 2. I'll let you decide which way you want to do it. I'll do 2 times 3. And then ask yourself, am I at the end of a branch yet? If the answer is yes, that must mean that you've got prime numbers. And in fact, we do have prime numbers. We've got a 2 and we've got a 3. So our pyramidal tree is done. Now, what do you notice between the two trees? You might notice that they both started with 18. Look at the ends of the branches. There's a 2 there's a 3, and there's another 3. So the prime factorization of this second tree could be written the exact same way. 3 times 2 times 3, or because of the commutative property, 2 times 3 times 3. Or, like a math pro using those exponents, 3 squared times 2. Because for the squared, we've got 1 3 times another 3. So it shouldn't matter how you decide to build your tree. You should always end up with the same prime factorization at the end. Let's try another one. Now let's try 40. All right, so like we said, there are lots of different ways to solve this. And what we're going to do is we're going to take notes on one way to solve it, and your task is going to be to figure out another way of solving it. So I'm just going to walk you through this process one last time before you're on your own to figure out your own factor tree and the prime factorization, which hopefully comes out the same as this. So if I'm thinking about 40, one of the most natural ways that comes to my mind to break it up in terms of factors would be to do 4 times 10. Maybe that was what came the most naturally for you too. Maybe you'll think of another way. Okay, so 4 times 10. I have to ask myself, are these numbers, 4 and 10, prime or composite? If they're prime, I've come to the end of the branch. If they're composite, I need to keep branching. These are both composite. So they both can be decomposed into other factors. For 4, I can do 2 times 2. And for 10, I can do 5 times 2. Awesome, okay? After every step, ask yourself, prime or composite? If they're composite, we need to keep branching. However, these all happen to be prime. So I can circle the ends of every single one of these branches. How's that for a perfectly shaped pyramidal tree? So the prime factorization would be written, if I just read it from left to right across the tree, 2 times 2 times 5 times 2. Now here's a challenge. How would a math pro write that? Can we use exponents? I see 1, 2, 3 2s. 2 times 2 times 2. I could do a shortcut there and say that's the same as 2 to the third power. Remember that 3 means that you see it 1, 2, 3 times. So 2 to the third times 5. Still have that 5 left over there. That is how a math pro would really write it. So I'd like you to write it whenever you're doing this kind of activity with exponents, whenever you can. You have a choice between tasks. Option number 1 is build a different factor tree for 40 and write its prime factorization. It should be the same as what we've got here. Maybe in a little different order, but it should be the same. So that's a way to check yourself and see if you did it correctly. So you may not start with the factors 4 times 10 and your first branches. Your first branches have to be something else. And you can't just go, okay, I'll switch them. I'll do 10 times 4. No, that's pretty much the same tree. So you can't use 4 and 10 as your first factors. Option 2 is a challenge task. Yikes! Come up with at least one real-world application for this lesson. In other words, so what? Why are we spending this time learning this lesson? When will you ever use this in real life? Now that doesn't mean, oh, it'll prepare me for 6th grade algebra. That's not real world. Real world means in a future job, not necessarily just as a mathematician, but a future job or a future activity that you can just do, sports, real world stuff. When would you ever use this? So you choose which task you would like to do. You can complete both if you'd like. If you do the challenge, you can think of it on your own, you can talk to people, and you can also do some research, maybe Google it, and see if you come up with some real-world applications. Have fun, and we'll see you at school.